Hello everyone, let's move on to question number 14 for the mock test CET for the subject physics. And we are looking at the question that says that a particle starts oscillating simple harmonically from its equilibrium position with a time period capital T. Now the question asked is what is the ratio of the kinetic and potential energies of this particle when the time is T is equal to T by 6. Now the options given to us are 1:3, √3:2, 3:1 and 2:√3, and the correct answer to this question is option A, that is 1:3. Now to solve this sum, we will quickly take a look at what is meant by simple harmonic motion, but before that, the only data that we require from this sum is the fact that we want to calculate the ratio at time T by 6. So let's save this data, so we need this for later. Now let's recall what happens in simple harmonic motion. They are telling us that this particle is oscillating simple harmonically. So let's quickly revise what happens. So let me take an example of a simple pendulum. It is the easiest thing to help us revise what happens in simple harmonic motion. Now what I'm going to do is I'm going to draw a graph of the motion of this simple pendulum. That is, I'm going to draw a graph of the position of this pendulum versus time. And I'm going to start with one side. That is, I'm going to start with this pendulum on one end and I'm going to call it as point A. And then this pendulum starts to swing, and watch how the graph is made as the pendulum swings. So we go from point A to the equilibrium position or the midpoint, and you see how the graph goes forward. From this point B, I go to the other extreme and you see how the graph goes forward. I'm back to the position on the graph that is on the x-axis. Now I'm going to go back, that is from point C to point B, and now finally from point B to point A. And this counts as one oscillation, and therefore the time period that I will indicate on the time axis is starting from point A up to the last point on this graph, and this will turn out to be the time period capital T, and this is the time period that they are talking about. Now the reason I do this graph is to remind you that the equation for simple harmonic motion says that this motion is represented by the equation x is equal to a sine omega t, and that's the reason I showed you this graph, to help you understand why is the graph of simple harmonic motion represented by a sine curve. So anyway, so this is the equation x is equal to a sine omega t that we're going to need. Now once I know that x is equal to a sine omega t, I start applying what I have been told in the sum. But before that, let me replace this omega with 2 pi by t, because we know that angular frequency omega is equal to 2 pi divided by the time period t. So I have this equation where x is equal to a sine 2 pi small t by capital T. Now I'm going to use the data that is given to me in the sum, that is t is equal to capital T by 6, and I'm going to put that data t is equal to capital T by 6 into my equation, and then I can write x is equal to a sine 2 pi small t by capital T. But instead of that small t, I'm going to put this capital T by 6. So I bring that from here and it becomes x is equal to a sine 2 pi by t into bracket t by 6. And when I do the correct cancellation, I get x is equal to a sine pi by 3. And we know that sine pi by 3 is √3 by 2. And this gives me what I want, that is x is equal to √3a by 2. Now the question you must ask is, why am I finding this x? You'll see shortly, but for now we have found what x is, that is √3a by 2. I'm going to need it, so I'm going to save it, and this is all I need to solve the sum, because the sum says that you have to find the ratio of the kinetic and potential energies, and this is exactly where I need x, because whenever you have a simple harmonic oscillator, the kinetic energy is given by half m omega square bracket capital A square minus x square, where a is the amplitude and x is what we have found, that is √3a by 2. So let's quickly substitute in our equation. I want kinetic energy. It will become half m omega square a square minus, and I need this x from what we have found. So I bring √3a by 2 down and I get the expression for kinetic energy, and it turns out that kinetic energy is 1 by 8 m omega square a square. This is my first equation. The next thing is I have to find the potential energy, and the formula for potential energy for a simple harmonic oscillator is half m omega square x square, where again I will replace this x with √3a by 2, which we found initially, and this gives me the expression for potential energy, which is 3 by 8 m omega square a square. This is my second equation, and now it's pretty straightforward. all you need is a ratio of the kinetic and the potential energy. So let's take kinetic energy from equation 1. So I'm going to bring kinetic energy this side. I have to divide it by the potential energy. Let me bring that down, which will be equal to the right side expression of equation 1. So let me bring it here, and the right side expression of equation 2, let me bring it down. And once you do the calculations, you will get that kinetic energy upon potential energy turn out to be 1 upon 3, and therefore the ratio that we require turns out to be 1 upon 3. So the final answer is that the ratio of kinetic and potential energies for the particle at time t by 6 is 1:3, and that's how you arrive at the correct answer. Thank you for watching.